Hey, welcome back after the lunch break. This is the OpenMP for Computational Scientists tutorial. Those of you that joined this morning, welcome back. For those of you that have joined for this afternoon, this morning we've spent a lot of time learning all about OpenMP and have done a lot of work working our way up from starting with serial Fortran all the way up to NUMA-aware, vectorized, parallel codes written in OpenMP that are going to run well and on our multi-core CPUs. So we've already covered a lot of things, and this afternoon is going to continue in that same vein. We're going to look at the support in OpenMP for targeting GPUs. This is a hands-on tutorial for those that are joining this afternoon. So there's going to be a mixture of me speaking and explaining things in a sort of lecture format, followed by exercises for you to try out the things that we've been explaining in the lectures. All of the material, all the slides and the source code is available on GitHub, and you can download it from there. It might be useful to follow along or have the exercises or some of this preliminary information open as well. So I think in one of the previous Q&As, there's a clickable link for this, maybe in the chat or the Q&A. Now, this afternoon, we're going to continue with using the Q&A part of Zoom for taking questions as you do the exercises. So use that over the chat. It's difficult to keep track of the chat and answer questions there. So ask any questions you have in the Q&A part of Zoom. There's a little button somewhere near the bottom for you to open the window for Q&A. So we're all going to be running on Isambard, and the GPU nodes that we're going to be targeting are these NVIDIA P100 nodes. Now this morning we were running on the CPUs, so this afternoon we're going to be offloading our parallel codes to the GPU so that we can gain some performance there because of the extra memory bandwidth available. So for those of you joining this afternoon, we can get you set up with an account, and I'll show you that when we get to the first exercise. So this is the plan for this afternoon. I'm going to spend a bit of time now explaining about how you're able to start offloading code and regions of your program from the host onto a GPU device or any other kind of accelerator device, and how you move data as well. So how you move execution and how you move data. And then we'll move quickly into the first exercise, which is going to be taking the Stencil code we've been working on this morning and getting it running on the GPU by transferring execution and data. Then after that, there'll be a lecture where I'm going to explain about the parallelism on the GPU and how it's exposed in OpenMP. We'll have a quick coffee break and then go into how you might optimize the data movement between the host and the device within OpenMP. And then finally, we'll put all of those things together, so applying the parallelism and the data movement to optimize the Stencil on a GPU. Get it running in parallel on the GPU and optimizing some of that data transfer. And it will be done by 4:30 UK time. So with that, I'm going to get started with the first part of the GPU material. We are now moving into some of the extra features that were introduced in OpenMP 4 and refined in 4.5. So we're going to be talking about the OpenMP target construct primarily, and all of the constructs that build upon that in order to deal with this heterogeneous compute node where we have different types of computing architecture all within the same node, a CPU and a GPU. So why might we want to use a GPU in the first place? Well, hardware is developing over time to give us these very highly parallel processors, and this is true of CPUs and of GPUs. But with a GPU, the approach has typically been to construct each processor out of a large number of simple cores compared to a smaller number of more complex cores that you'd imagine, like in a CPU. In doing this, they often have an increased number of floating point operations. So a NVIDIA V100 GPU has nearly twice as many floating point operations per second. So the amount of double precision compute that can happen over something like a Skylake. But also, GPUs have often taken on board the latest innovations in memory technologies, in particular using things like high bandwidth memory. And CPUs have only just started picking up that mantle. We've seen that with the Fugaku supercomputer in Japan, which uses the Fujitsu A64FX ARM-based processors. They are now including high bandwidth memory on a CPU socket. And as most of our codes are main memory bandwidth bound, being able to leverage this memory technology, the high bandwidth memory, has only been possible with GPUs until now, and it's starting to creep into CPUs at the moment as well. So let's have a little kind of case study of what GPUs might look like. And for this, we're going to use NVIDIA. And in this slide, I'm going to be using a lot of NVIDIA definitions for how they construct their GPUs, what their architecture means to them in their own language. So a GPU is made up of many cores, and they're cores like we think of them as a CPU core. NVIDIA call those streaming multiprocessors instead. And a V100 GPU has 80 of those, 80 SMs, and a P100 has, say, 56 SMs. So compared to the CPUs, that's an awful lot of cores on that particular socket, many more cores on the GPU. Each of those SMs has 64 single precision CUDA cores. Now, this is quite unfortunate that NVIDIA has chosen the word core to define what is essentially a vector lane, whereas the CPU idea of a core may have vectors within that. So it's important to think that when you hear the term CUDA core, they are organized as these 2 vector units in blocks of 32 CUDA cores together, and they call them warps. So the takeaway is that GPUs look a lot like CPUs in many ways. They're really vector architectures that are made up of these smaller blocks which execute together. So we have these very wide vectors, 32 or 64 wide, and we have one of those on a large number of cores. And the cores are somewhat independent, but the SMs are somewhat independent, but the cores operate much more like a vector unit than an individual core on a CPU, for instance. Another thing to notice is that GPUs are typically classified as throughput optimized. So it's all about getting a large amount of stuff done in a given amount of time. Whereas CPUs are often optimized for latency, things like caches and that sort of thing, and the deep cache hierarchy that CPUs have got really help it become optimized for latency, whereas GPUs is all about being tolerant to long latencies, so they sacrifice a large latency to do things like read from memory, for a throughput-based approach where you do lots and lots of things at once, lots and lots of operations in parallel, and overlap them with each other, so you hide all that latency. It's trading off throughput for latency, and that's where the high memory bandwidth can help. Now, to do that, we need to exploit lots and lots of parallelism in our applications in order to be able to do that on a GPU. So if we think about the V100, this is over 5,000 individual processing elements, and each of those is going to need multiple bits of work in order to overlap with each other to make best use of that throughput optimized architecture. So the key message is that we need to find a massive amount of parallelism in our applications in order to be able to exploit the concurrency that's available at a hardware level on the GPU. So that's GPUs in general, and we'll now move on a little bit and talk about OpenMP and how GPUs and things like that are seen as far as the OpenMP model. Like many other heterogeneous programming models, things like OpenCL and SYCL, OpenMP has this model of a host and a device. So we have a host CPU, which has its CPU memory, and connected to that CPU is one or more devices. And that device has its own memory that's attached to it. This aligns with the actual hardware. We have our CPU with the DRAM attached. We then have some PCIe or NVLink or something that connects the CPU to the GPU. And then the GPU has its own memory. It has HBM or something like that embedded on the accelerator card itself. So this model, although it's an abstract model in the sense that it is just defined an OpenMP's view of the world, it does map to how these devices are actually connected into the processors and into the nodes as well. So the target execution model for OpenMP. Well, execution begins on the host, and there are 0 or more devices connected to the host, and the memory spaces are not shared between the host and the device. Now, with OpenMP, it's typically called a shared memory programming model, and that's true for the threads on the host CPU. But there's no, the memory isn't necessarily always readable or anything or accessible from the device and the host. There has to be some movement of data between the host and the device. So the memory spaces are not shared. It's not a free-for-all necessarily, although there's some features in OpenMP5 that do allow for that to be the case if the hardware supports it. So the memory model, you have these distinct host and device spaces. In OpenMP, some data is going to be automatically copied between the host and the device and back again. And there's also a lot of controls for explicitly copying data as and when you need it. So for the execution model, we start on the CPU with our serial program or even our parallel OpenMP program on the CPU. But at some point, our single host thread is going to want to transfer execution to the device so that the execution of a particular part of the code can be executed on the GPU device instead. And for that, we use the target construct, this target directive here. So in Fortran, we have our Sentinel symbol and then OMP. In OpenMP, all of the majority of the ways you write OpenMP code is with these compiler directives. So we have our target and end target, and any code any of our Fortran code that exists between the target and end target is going to be offloaded to the GPU. It's going to be executed there instead of on the host. We can have a number of clauses to the target directive, and they're often used to specify some of this data movement between the host and the device. It's important to know that in terms of the execution model, that the host is going to remain idle until the target region completes. So when we have the target region, execution is going to go to the device, and the host will sit there and wait until it's finished. Now, the exact semantics of how all of this works is based on tasks. And in the repository, there's a slide deck that talks about OpenMP tasking. If you go to the slides and PDFs and then some older PDFs in there, you'll be able to have a look and see in tutorial material like this what the OpenMP tasking model is like. But I'm not going to go into too much detail with that for here. All that you sort of need to know is that the offload is all synchronous. So the host offloads the device, waits till it's done, and then execution then continues on the host. So programming a GPU is often useful to think about this in kind of two parts. There's the parallelism that we need to expose on the GPU, and then also the movement of data between the host and the device. So often programming the kernels and the loops themselves, so this is writing the parallel loops and things, this is often the easier part of those two things. It's often the easier bit to get right, especially if you've already got a highly optimized CPU implementation. Most of the development and programming time, in our experience at least, is making sure that we optimize for the movement of memory between the host and the device, making sure that the data transfer between the two distinct memory spaces is as optimized as possible is often where we spend most of the programming time. As I just said, a lot of the reasons for this are if you have already got a highly optimized CPU code, and you found lots of parallelism, mapping that onto the GPU in terms of the parallelism is quite straightforward. And also all those optimizations, and some of them I talked about this morning, particularly around memory layout and for memory layout for vectorization, They often apply to GPUs in exactly the same way. Things like having coalesced memory accesses that would support good vectorization on the CPU are going to really help you have good performance on the GPU as well. So we're going to take this approach and we're going to break down the two parts, the parallelism on the GPU and the memory movement on the GPU as well. So to start with, how can we actually get something running on the device? Well, I've been through this briefly, and we have this target construct. So we go OMP target, and all the code in there is going to be offloaded to the device. Now, it's important to note that what the device is going to execute, all of that code is going to be in serial. We just launch a single thread on our GPU, essentially. We need other constructs to be able to define and expand the parallelism that we're going to have to exploit within that target region. So we're going to need to launch some parallel things within the target region, and we'll come on to that in due course. So that's important. We stop executing on the host and we start executing on the device, and it's serial execution on the device. We can allow the host to continue doing something else in the meantime. We can have this idea of an asynchronous offload of a target region. And for that, we would add the no wait clause to the target directive. So one of those clauses would be the word no wait. This means that the OpenMP runtime packages up that target routine as a task that can then be run as and when it feels like it, and the host can continue executing beyond the end target directive and do something else. For instance, it could do some header exchange, or it could do some file IO, something like that. All the tasking mechanisms that are built into OpenMP are then used to wait for all of those target regions to finish. Typically, you would use something like task wait, and that would wait for all the target regions to finish executing. The other clauses that you might put on the target region are all about memory movement, which I'm going to come on to in a moment. So it's important to remember that we really have these two distinct memory spaces, the host memory space and the target memory space. Now, all the host memory space is shared between all the cores on the host, and all the memory space on the target is shared between all the parallel executing things on the target. Unless we specify any sort of data sharing or something like that. But there's no automatic sharing of the memory between all of the memory of the host and all of the target. So what we have to do is we have to use a combination of the implicit movement and the explicit management of that memory movement that's available in OpenMP. And this is pretty much the most complicated part of the offload specification. If you're feeling very brave and fancy reading the OpenMP specification, there's quite a lot here in the spec that talks about how data is implicitly mapped and explicitly mapped between those two memory spaces. It's also important to make sure that we get this right. Memory movement is often the performance killer in our applications. If we use this NVIDIA V100 as an example again, it has 900 gigabytes a second of memory bandwidth available to it. Now that's between the parallel things on the device and the high bandwidth memory on the device. If we plug it into our CPU node with PCIe, we're only going to get 32 gigabytes a second peak bandwidth across the PCIe. So the transfers between the host and the device are relatively slow. So we need to minimize them to make sure that we do as few of them as possible so that we can keep the data resident as much as possible on the GPU and avoid being bottlenecked by this lower bandwidth that we have between the two memory spaces. Okay, so how can we get data from the host to the device and back again? Well, we need to map the data between the host and the device. And the way OpenMP does this is it uses the variable names, and really it's the pointers, the implementation of where that exists in memory to map these things. So variable names really exist in two places at the same time, essentially. They exist in host space and they exist in device space. And the compiler sorts out which one you mean when you use them in your code. So in this example of the code here, I might have the first line here is X, and that's an array on the host. But inside the target region, when I use the variable x in my program, it's going to be referring to the variable x, the array x that's in the device memory space instead. And that's because it's inside the target region. So it's left up to the OpenMP runtime to work out when x is in host memory or when it's in device memory. So really, this is like having two separate arrays, the host x and the device x, and they are on the device and host and device respectively, based on their sort of prefix there. But we don't have to have these two copies explicitly in our code. It's just all wrapped up into the model that we're buying into with the OpenMP target offload. So when might data move? There are very specific places that data will move. And by the time we get to this afternoon, I will have gone through all of these. So the first is on the beginning or the end of a target region. So when we can transfer execution from the host to the device, that's a point at which data may move, either at the beginning or at the end. We can also specify places where data will move explicitly. These are these target enter and exit data constructs, and also of a target update construct. Those are the specific places that memory can move. So let's talk about the default behavior. OpenMP has a lot of implicit mapping between the host and the device. So the default behavior when we start a target region is that any scalar variables are going to be mapped first private. So this means if you have any scalar values that are in your code outside the target region, inside the target region they're available. There's going to be a local copy to every parallel thing that's running on the GPU, every parallel thread. And each of them has its own local copy of that it can freely update. It's going to contain the value that it was on the host because it's first private. But what this does mean is that if you update it, it doesn't get copied back to the host. If you're familiar with any of these other heterogeneous program models like OpenCL, this would be like passing in the variables as a kernel argument, so like a function argument passed by value. So it saves a memory copy because you can just load it as part of the offload information to the target. So that's scalar variables. They're all mapped first private. Now, stack arrays, these are sort of local arrays that in Fortran that don't have the allocatable property. These are just arrays that you just make of a given size. These are going to be mapped to from. This means that when they enter a target region, they're copied and all the data in there is copied from the host to the device, and it's available in the shared memory of the device to be used throughout that target region. But then when that target region ends, all those stack arrays are then mapped from the device back to the host at the end of the target region. So scalars are going to be copied automatically. Stack arrays are going to be copied to and from automatically. But heap arrays, things with the allocatable property, these are not mapped by default at all. And we, as programmers, need to map these heap arrays ourselves. And to do that, we're going to be using this map clause. And this specifies information about the transfer of data between the host and the device on the target region. So let's say we have this array A of length n. So it's going to be from 1 to n in size, and we have a scalar x. In Fortran, it's often very convenient because the size of that array is generally embedded within the type. The array itself knows exactly how big, what the extent of that array is. So in Fortran, you often don't need to specify the size of that array that you need to copy back to the between the host and the device in the map clause. We could just give it the variable name. If you decide to write OpenMP programs in C, whereas arrays are simply just pointers, you do need to specify the amount of data to copy. But with Fortran, you can just give it the array and it sort of remembers how big, how much data is in that array. You can use array slicing as well, and that allows you to just copy portions of the array, and that will work as you would expect. It uses a similar notation in OpenMP inside the map clause to the Fortran array slicing. Assume size arrays get a bit thorny, but it's best not to use assume size arrays inside the low level parts of your kernel anyway. You can fairly straightforward in Fortran specify the size of those arrays so that the compiler has the very best job of knowing what the extent of those arrays actually are when you want to have a low-level loop in your code. So we have these arrays and scalars that we want to explicitly transfer between the host and the device when we're offloading, when we have the target region. So we have our target region, the OMP target, and end targeted at the end. And we have our map clause, and inside those parentheses, we're going to list all the variables that we need to transfer the data between the host and the device. It's doing a memory copy between the two spaces. So the direction of the transfer is always from the host's perspective. It's always going to be from the host to the device, or from the device to the host. It's always the host that has the last say in the perspective of the direction. So as well as specifying the variables in this comma separated list, we can also specify this tag just beforehand with the colon, and this specifies the direction of the transfer. So let's have a look at map 2. Map 2, let's say we've got A and X. This means that on entering that target region, the array A and the scalar X is going to be copied to the device. So from the host to the device, and that's at the start of the region. Now, then there's map from, and we can do the same thing. This means that when we exit the target region, so when we have that OMP end target, data is going to be copied from the device back to the host. So that means that it's going to move and get copied. Any updates we've had on the device is going to come back and be visible on the host. But what this does mean is that at the start of the target region, although data will, the memory has been allocated because there's space for it, because we know it exists on the device, because it appears in a map clause, the actual values that the data takes, that A and X, are going to be uninitialized. It's not going to contain anything, any particular values. So if we initialize A on the host, but don't copy it to the device, then if we have it appearing in one of these map clauses, there's space for it, but it contains just unallocated data. Now, sometimes we want this behavior, so we want to copy data to the device, update it, and then bring the updated copy back. And this is where the to from mapping comes in. So we could map to from the two variables A and X. And this is exactly the same as applying both of those maps together, the map to and the map from. Finally, we may want to allocate some memory on the device, but it's only ever going to be seen within that target region. We never need to bring it back to the host within that target region. For that, we can use the alloc identifier on the map. So we could map alloc A, and that would allocate an array the same size as A on the device, and would be able to access it using the variable name A. So this isn't going to copy anything from the host. It's not going to copy it back at the end of the target region either. And the value inside that is, again, uninitialized. If we have allocated it on the host elsewhere, and we're in some of the more unstructured ways of mapping data, then we can copy the values of A back to the host with something like update, for instance. But we'll come to that after the coffee break. So that's it. We're here. We're already at our first exercise. So at this point, we are going to take the 5-point stencil code that we've been looking at this morning. And for those of you joining this afternoon, there is a file there called stencil_numa.f90. That's the place where this morning's attendees should have roughly gotten up to. This is the NumaWare parallel optimized 5-point stencil. So we're going to take that code and we're going to port it to the GPU, and we're going to use the information that we've had so far. So the two things really to do in this exercise are going to be using the target construct to transfer execution of the main kernel to the GPU. And then we're going to be using map clauses to transfer the data at the point of the target transfer, this target region, to map the data to and from the device. There's two arrays, a current array and a temporary array, and we can use map clauses to make sure that those arrays exist. In the Stencil code, those arrays are allocated on the heap. They're allocatable Fortran arrays, so we must use these map clauses in order to be able to transfer the data. So that's over to you, the exercise. For those of you joining and don't have an Isambard account, I'm just going to show up some slides that show you how to connect. For those of you that do, please get started with the exercise. We're going to come back at in about half an hour or so at 25 to 3, so at 4:35, and then we'll start talking about parallelism at that point. So good luck with the exercise. Please use the Q&A. I'll be starting to look at that now to ask lots of questions. I'm just going to switch the slide deck over so that we can, for those of you that don't have an Isambard account, can find out that information. Okay, so for those of you joining this afternoon, please go to this web page here, this tinyurl.com/openmp-2020. When you get there, there'll be a short form to fill in that will give you a training account on the Isambard supercomputer, as I introduced earlier. With that number, it'll give you a number, and then you'll be able to log in to the gateway node using this command on the second point, ssh to isambard.gw4.ac.uk. And the username you have is br-train and then a number. And that number will be whatever that form gave you in step 1. The password for all the accounts is as on the slide, OpenMP UG for user group, and the number 20 with UG as capitals. So that SSH command will get you onto the gateway node, and then you need to log on to the login nodes of the part of Isambard we'll be using today. So you'll SSH into Isambard, and then you will SSH into phase 1. And once you're there, you're in the right place, and you just need to change directory into this OpenMP for CS. And in there is the slides and the exercises. In the slides directory, there's a PDFs subdirectory that contains the PDFs that I'm showing you as well. Once you're there to use Isambard, you can just build all the exercises. The one we'll start, if you're starting today, is the Stencil NUMA. So you could just type make stencil_NUMA. That would build that CPU binary. And then you can submit a job. Now you might need to change the job submission script to be the right binary name. But if you're working from this morning, it's probably just going to still be the same stencil. So update that file, submit stencil. And then to start running your code, you would type submit qsub and then the job submission script submit stencil. That will then run that inside the queue and produce an output in a file. Now you can see how your job is progressing through the queue with this command on line 8, qstat -u $user. But the jobs tend to go through very fast. So by the time you've typed qstat, the job's gone through anyway. The output is always going to be in a file, and that file is going to be called stencil or stencil, and then a period character, full stop, and then a lowercase o number, like a character O, and then a number. And that number is the job number that step 7 here, the qsub command returned you. So you can have a look in there and see the output from the job that ran. So I'll leave this up for a little while before switching back over to the exercise slide for those of you that need this URL to get yourself set up with an account. Please use the Q&A in Zoom to ask any questions. I'm going to switch over to that now and start answering any questions that have come in. And we'll start going back to talk a little bit about this exercise and move on to the next part of the day at 14:35. That's UK time. Yeah, there's a great question just come in on the chat. You don't need to change the queue name or anything. Just keep using the submission scripts. That's going to get you on a node with the GPU. So you'll just be able to build your codes as before, and just nothing needs to change in your programming environment to start running on the GPUs. It's all been set up for you. On a Cray system, this is generally made very straightforward. We don't need any extra compiler flags to build OpenMP for the GPU. We just need to load some specific modules, which have already been loaded for all of the training accounts. If you type module list, you can see the sort of modules that get loaded for you to take that sort of information away to your own Cray systems. With other compilers, you may need to have some additional flags, and there's information about that with all the compiler documentation about what flags you might need for those. Still plenty of time for this exercise, about another 10 minutes or so before we start the next session. I might just go through the things that I might have changed just a couple of minutes before that. So in just under 10 minutes, I'll show you how I might have done this exercise, just using the knowledge that that I've shown you so far. And then we'll move on to the target parallelism section of this afternoon. So another nearly 10 minutes before we come back. Okay, welcome back. It sounds like a few of you have managed to get some code successfully built and running. I'm going to show you how I might have done this myself, just using the beginning. So let's start with this. Hopefully you can see my terminal here. So this is the Stencil NUMA file, and this is where what some of our code might have looked like after this morning. And to start with, I took away all of the parallelism around the kernel, just because we were just going to use the things that we've started with so far. So around this kernel, I've added the Sentinel OMP target to say that this nest of loops here, we turn on line numbers between lines 16 and 21. Those are the loops that I want to start running on my GPU. And to say that they are ending, I have to have the end target as well to show that that's where the execution needs to return back to the host at that end target statement on line 22. So that's the execution taken care of. I now need to deal with the mapping. So I now have two arrays, A temp and A, that are used inside this loop. So I need to make sure that they are copied from the host memory space to the device memory space. So to do that, I'll have the map clause with a to from instruction in there, and then the arrays listed A temp and A. Now, luckily, we're in Fortran, and because of the way I have specified the size of those arrays on lines 8 and 9, those arrays, Fortran knows how big they are. They know that they go from 0 to nx plus 1 in each dimension. So the compiler is fully aware of the size of those arrays. If they weren't, I might have to use the array notation to specify the length of those arrays in each dimension. Now, at this point, I knew that my execution on the device was going to be in serial. So I knew that when I do this reduction of total on line 19, I'm going to be updating that variable as well. So to make sure I get the answer back, I also added the total scalar variable to my map clause. Now, if I don't map the scalar total, it's going to be mapped as first private. This means that it's going to be copied to the device, but not copied back, and there's no way for me to get that result back at all. So by mapping it, it's going to map it into the global memory of the GPU device, so that I'm able to have them see the updated value back on the host. Whereas if it's just a first private variable, I'm not going to be able to see that. So I've had to map the total to from as well. So that was all we were sort of looking at doing in this first exercise. We've transferred control from the host to the device, and I have mapped the data from the host to the device as well and back again. So at this point, the code should still behave correctly. I'll still have a code that computes the total value correctly because it's just in serial, and it's going to still do the update and update it back. But I'm just using a single thread on the GPU, which is really not going to be efficient at all. And that's where we come to now. We're going to start talking about the parallelism available on the GPU and how to expose that and take advantage of it using OpenMP. That's going to take us up until 3 o'clock before we'll break for coffee at that point. So back to the slides now. Hopefully that's switched over. Looks like it has. Great. So I'm going to start by foreshadowing a little bit and just saying, in general, if you have a parallel loop that you'd like to run on the device, you're pretty much just going to be able to get away with saying target teams distribute parallel do, and possibly there'll be a SIMD on the end of that as well, but I'll talk to that in a little bit. So we have our parallel loop, a do, and inside there is our loop body. And above that loop, we're going to have this big long construct. Target teams distribute parallel do. And as before, we need to end the target region with end target teams distribute parallel do as well. These are using the combined constructs in OpenMP, and they are there as a shorthand. We could write all of these things on individual lines, but we could also write them as a single line and hopefully have a way that we can, they mean all things together then. So we're going to walk through what each of these constituent parts mean. Now we've already seen what target means, so we're just going to go through the teams, distribute, parallel, and do, and talk to SIMD a little bit as well. It's worth saying at this point that if you just have a large parallel loop, not using a combined statement like this with all of these parts to it can have very severe performance degradation issues that you might run into. If you start breaking up this particular construct, you might find the compiler has to take different paths and parallelize the code in the way you've asked with this, with the separate parts of the construct. So if you just have a big parallel loop that you'll want to run on the target, this big combined construct is typically what you'll do. Note it's often convenient to have an OMP target and then OMP teams distribute parallel do on a separate line, so we can have our code looking clean, where we can have the map clauses on the target and then the parallelism expressed on the following line. And that's fine. You're not going to run into performance issues with that approach. It's just if you start breaking up the teams and the parallel do and that sort of thing, we have observed some performance issues in the past. So let's talk about teams. That's the first part of our big directive. So let's look at target teams with some code in the middle. So we talked to this a little bit this morning. When you make a lot of threads on the device in OpenMP on the CPU and on the GPU, all of those threads are grouped together in a team. You have a team of threads, and this is true on the target device as well. The OpenMP threads are grouped into one or more teams. This is really important because of the synchronization constraints that teams impose. So in OpenMP, you can synchronize between threads that are within the same team, but you cannot synchronize between threads in different teams. This is true of other parallel programming models as well. Things like OpenCL, you can synchronize work items within a work group, but not between work items in different work groups. And it's a similar approach and a similar kind of model here. So threads within a team, we can use, say, an OpenMP barrier or the implicit barriers at the end of do loops, those sorts of things. We're allowed to synchronize between the threads within a team, but we cannot synchronize between teams. In fact, we don't even know what order those teams may execute in. And this is why these sort of forward progress guarantees are quite weak between teams, so that this means that we don't have the facility to synchronize between different teams. However, when we end target, so we must exit the target region, that is when we do synchronize between teams, because the whole device performs that whole device synchronization when execution returns from the target device back to the host. So at that point, we know all our teams have finished executing. But before that, there's no way to get this synchronization. So we have our threads, and they're grouped into teams. And groups of teams are called, is called a league. We have a league of teams, and there's a team of threads. So our target construct, OMP target, this offloads serial execution to the device. And with the teams directive on the target directive, this creates a league of teams. So when we have target teams, we're going to create a league of teams. And then we haven't said how many threads are in each team, but actually there's just going to be one, the main thread, the master thread. This is in OpenMP 4.5 terminology. There's going to be a master thread in each of those teams, and it's going to redundantly execute the code between these two statements. So this is the first part of our parallelism. We have target teams. We've transferred to the GPU. We launch a league of teams, and one thread in each of those teams is going to be executing the same code in this block. We've seen a similar idea if you just have a parallel statement where without any of those work sharing things like parallel do, where each thread just executes exactly the same code. So here it's one thread in each team executes this target region on the device. So how might this look in this sort of cartoon picture? So target teams is going to create a number of teams on the GPU. These are these big rectangles on the slide. Say we make 4 teams. I've got a league containing 4 teams. And each of those teams is just going to have one thread in this main or master thread. So each of those threads is going to execute the code block that's been defined by the target and the end target teams. And all those are going to do exactly the same code because we haven't necessarily specialized it. So this is how our parallelism looks so far. We've gone beyond serial now because we have a league of teams that's executing some code. So what if we have a loop? We want to work share that loop across the team so that each team gets its own part of the iteration space. This is a similar idea to a parallel do, where we want to spread the work between the threads of a team. Now we want to share the work between teams. So to do this, we say target teams distribute, and we have to put this before a do loop so that we have a loop in which to partition that iteration space. It's going to use a static schedule, which is basically breaking that iteration space up into n divided by the number of teams, and each team is getting a chunk of that work. So this is now being able to distribute a loop and splitting the work to do within this target region between these parallel teams. We still only have one thread in each of our teams, this master thread, and that's going to execute each of those chunks of the loop that is being executed. So back to our picture. Let's say we had a loop that goes from 1 to 100, do I equals 1 to 100. And we have our target teams distribute construct. So again, say just for the slide, we have a league of 4 teams. So our distribute is then going to break that iteration space of 100 into 4 and give a chunk, a contiguous chunk of each of that iteration space to each of those teams to execute. So you can see that I've annotated each of the teams, the rectangles with a range, I equals low to high. Again, each team still only contains one thread, but each team is now going to be computing a different part of this iteration range. So we're now starting to build up the parallelism for our do loop. So we're now not doing redundant work, we're sharing the work out between the different teams. We now come to parallel do, and luckily this has exactly the same semantics as it does on the GPU as it does with the CPU. So parallel do means the same on the CPU as the GPU. So parallel launches threads within the team, and the do distributes iterations of that loop across the threads in a team. So in our construct, the target teams distribute parallel do, we have already distributed the loop between the teams. Now the parallel is going to refer to each team. Each team is going to launch a number of threads, and the do is going to share those iterations that have been distributed to each team across the threads that are now available in that team from the parallel. So it's perhaps more straightforward to show this with this cartoon picture again. So at the top, we have the situation as before. We have target teams distribute that's going to share 100 iterations between 4 teams. And you can see the range of each team at the top. When I have parallel, let's say that's going to create 5 threads, 5 OpenMP threads per team. So I now have 20 threads running in total, 5 for every team, lots and lots of threads. This is how we get that massive parallelism that we can then use on the GPU. So that's the parallel. We've spawned all these threads in each team, and then the do is going to is going to share the work share the iteration of the chunk within each team across the threads in that team. So using the indexes within each rectangle here, that's within the team, we can see that each of the threads numbered from 0 to 4 is going to get 5 iterations of the loop. There's 25 between each of the 4 teams. So we can see that the first thread in the first team is going to get, say, iterations 1 to 5. So this is breaking up the share of the iteration space that was distributed to each team by the distribute construct, and it's work sharing that with the do construct between all the threads in the team. So in this way, we have lots and lots of threads now. These are OpenMP threads, lots of those launched on the device. This is why having this hierarchical parallelism built into the language and the devices too is very powerful. We have expressed a lot of parallelism here. So we can also use the SIMD construct, and this is valid on the distribute parallel do as well. In general, we tend to use target teams distribute parallel do SIMD. Sometimes having the SIMD in there as well is fine. OpenMP just says that the SIMD clause must mean that SIMD instructions are generated. That's what it says in the specification. So there's some implementation details that differ between different compilers, and sometimes compilers ignore different parts of the construct depending on the situation. I'll come to that in the next slide, where we talk a little bit about how we might map OpenMP parallelism, the league of teams of threads of perhaps vector instructions, onto GPU, the GPU parallel models and the hierarchy that's actually available in the hardware. But in general, using this big construct, target teams distribute parallel do seems to be the most portable solution. Adding SIMD in can sometimes help with that portability as well. So OpenMP defines 3 levels of parallelism. We have teams, we have parallel threads within a team, and SIMD, and it's a SIMD thread. So this is a proper nested hierarchy where we can have a league of teams, and each team has a number of threads, and each of those threads may be executing vector SIMD instructions. So you can see how this maps to, say, like a CPU architecture, for example, with hyperthreads. We can have a team of threads on every core. Within each core, there's a number of hyperthreads or multi-threads or something, and they could be the 2 threads, maybe, or 4 threads within each team that exists on each core. And each of those threads is allowed to execute SIMD instructions. So on a CPU, there's this, you can see how there could be a 3-level hierarchy of parallelism available. But on GPU hardware, it's however you want to expose that, there are a number of ways you can do that. There really tends to only be 2 levels of parallelism that's generally exploited. First of all, there's these compute units, and these are those cores, these sort of SMs that I showed at the start of this afternoon. And then there's the processing elements within each compute unit. And they could be the CUDA cores, for instance, as I explained. Now, they might have some hierarchy built into them where you might want to target them as say, SIMD or whatever, but essentially there's just these 2 levels. There's cores and then elements within each of those cores or compute units. So with OpenMP, the implementations of OpenMP actually have a lot of flexibility in how they might map OpenMP, these parallel concepts of teams, threads, and vectors, to the underlying hardware. It's not stipulated what each one of those has to mean in hardware, and this gives the compilers flexibility to map the right ones to the right bits of hardware at the right time. It's important to know that, that sometimes the mapping may change depending on the context, and I'll show some examples of that. So let's talk about LLVM-based compilers, and many compilers now use the LLVM project as sort of a watering hole. They contribute and gain enormous benefit in both directions from basing their compilers off of the technology in LLVM. And this means that any improvements and design decisions and mappings and things is often common between lots of compilers. This is true of the Cray compiler since version 9, CCE 9 and above. And today we've all been using CCE 10. So these things apply for the compiler as well. Now, obviously, LLVM is still developing its Fortran capability, and Cray have helped there. And they use their own front end and some of their own OpenMP runtimes for their compiler with Fortran and OpenMP targeting GPUs. So in these LLVM-based compilers, OpenMP teams are typically associated or mapped to sort of overload the word map. They're associated with compute units. So we might map or associate each OpenMP team to one of those compute units or SMs in NVIDIA language. We then might map or associate each of the threads within a team to each of the processing elements within that compute unit. And with LLVM, typically this SIMD construct is ignored. The Cray classic compiler, which is what the Fortran is based on, tends to map the SIMD instead to the processing elements. That's instead of the threads, the OpenMP threads to processing elements. But this is changing over time. And as their compiler is going to be moving more and more LLVM based, we'll find that we'll be reverting to the teams and threads approach with that. So let's consider this when we look at the teams distribute construct. So what we find, this is saying that the loop iterations should be distributed between teams. We're not specifying anything else. We're not saying how many threads. We're not specifying to launch any threads within each team. So we just have a single thread within each team. Now we can't synchronize between teams. That's defined by the semantics of OpenMP. So when we write teams distribute, what we're saying is that all iterations are independent. We are not able to synchronize, so we can't assume that we might be able to. So we're telling OpenMP this loop has no dependencies between any of the iterations of the loop. Everything's independent. So this means that implementations can and will change that mapping, and they can map this to exploit all the parallelism across the whole GPU. So the mapping I showed on the previous slide is going to be slightly different for teams distribute alone. Because everything's independent, the compiler will use that information and then share the work across the whole GPU. So rather than, so we'll find that OpenMP teams are now being mapped to processing elements instead of compute units. And it doesn't really matter how those work items or threads or CUDA threads are going to be grouped into the thread blocks or work groups or how they're arranged on the compute units. It doesn't matter, that's implementation defined, because there's no synchronization between any of the between the threads at all, between those teams at all, because it's not allowed. We get this large parallelism. So this behaves a lot like sort of a SIMD auto vectorization approach, where we're saying all of these iterations are independent, and it just gets mapped to as much parallelism as is available on the device. So there's more than one possible mapping or association between the world of the OpenMP parallelism and the world of the hardware, and how those things may be mapped and associated with each other. So sometimes you need to find out what is happening. The first place to look is in the compiler documentation. Maybe they've explained what they do, and Cray has done this. If you type man intro_OpenMP, they have a very short man page that explains how their target is what is going to be mapped and associated for the different constructs and the rules that they apply in the C and the Fortran compiler. You can also have a look at the compiler output, and it will tell you how it's mapped the parallelism that you've exposed in your OpenMP program to the underlying hardware. And in CCE 10, there's the -rm flag, and I've put that in your make files already. This will give you a .lst file, a listing file, which you can then go through, and it annotates the source code with a big key and kind of ASCII information that explains exactly what optimizations that compiler has been doing, including offloading to the GPU and how it's associating all of those parts that they've exposed, the OpenMP teams and threads and SIMD with the underlying hardware. Finally, you can also profile your code and see what it's doing and how it's being mapped under the hood. So because we're using some NVIDIA GPUs, we can use NVProf. And this will profile our code and give us some high-level information about each of the parts. How much time is in memory movement, how much time is in each of the target regions. But if we have the print GPU trace flag, this will show us a timeline view in text of all the operations that happen. And included in that is the number of threads per block and the number of blocks. These are NVIDIA terminologies for how that parallelism has been arranged in the underlying CUDA-like implementation. So if you can combine those information of how many threads are running in each block and how many blocks you have with the knowledge of what pragma you had and how big your loop was, you can start to piece together what association you got between OpenMP parallelism and the underlying hardware. Now, understanding this is slightly complicated, but it can be important to try and understand what the compiler is doing. But as I said before, ultimately, just finding all the parallelism and exposing it at a single level with a large parallel loop generally is going to get you very good performance on a GPU, because you just have a single pragma and the compiler is free to choose the association between the elements of the OpenMP hierarchy of parallelism and the underlying GPU. So with that, we've come to the coffee break. I'm going to stick around and take some questions after on the Q&A on Zoom. So if you have any questions, I've seen there's been a couple coming in. I'm going to sit and answer some of those questions and grab a coffee. Do take some time away from the screen. There's a lot of information that we're going to go through, and it's good to step away from the screen. So we're going to start back at 3:15 in 15 minutes. And with that, I'm going to carry on with the lecturing to talk about optimizing the data movement. So we've pretty much finished the discussion of parallelism. I'm now going to show you how to optimize the data movement. And that will then equip us with all the tools that we need to finish the exercise off, to build on the Stencil code that we had before, which is now running on the GPU, but we now need to make it run in parallel and optimize the memory movement associated with that. So I'll see you in about 15 minutes at 3:15 UK time. Okay, welcome back from the coffee break. I hope you've all managed to get a breath of fresh air and a hot drink and all of that. We're now into the last half of the tutorial this afternoon. We're going to start by continuing by explaining the last bits of OpenMP I'd like to go through today. And this is how we're going to optimize the data movement between the host and the device. As I motivated earlier, this is a really important part of the of programming of things like GPUs. So we've learned in the first part of this afternoon about the transferring execution and the mapping of data and some of those implicit rules and the explicit ways and directions that you need to map and how you map arrays and things. And then we've looked at the parallelism just before the coffee break. So how to express this massive parallelism with teams and threads and SIMD on GPUs. So this final piece of the puzzle is moving data when you wish and not on every single target directive. Now, the motivation for this is a kind of sketch of lots of scientific codes. We're going to initialize some arrays with however we need to do that. Then we're probably going to have some sort of time step function maybe that loops over a bunch of update routines lots of times, maybe until convergence or until we've simulated enough time steps or things like that. And within each time step, we're going to update any arrays and any data that we have. The point is that the scientific codes tend to initialize data and run lots of kernels lots and lots of times, so lots of target regions. And in general, we don't really worry about the initialization cost, because relative to the amount of time that we spend actually executing our code, it's a small percentage of runtime. So the way we currently have written our code is, if we're in MPI, what we'd essentially do is we'd run part of our code with something, and then we'd do a big gather and scatter to reinitialize the data every iteration. Now, obviously, we know this is really not very optimal. And the same is going to apply between the host and the device memory spaces. as we've implemented so far, we're copying data between the host and the device for every iteration inside the loop inside our small 5-point kernel. We're just every time we get to the target directive inside just above the nested do loops, we're going to be moving data between the host and the device and back again at the end. And that's pretty wasteful. We just need to leave it there throughout the entire time step loop and copy it back once at the end. So as I said before, there's some very specific places that data transfer will happen in an OpenMP program that uses these target directives. And one of those places is at the start and end of every target region. So every time you have an OMP target, that's when data is allowed to move, be it implicitly by the rules or explicitly with the map clauses. So what we actually would like to do instead is sort of set up the device data environment, set up some arrays and some data that exists on the device, run through lots and lots of target regions, and then copy back any data we need once we're done. The idea is that we do not want to copy all the data every iteration. That is, we don't want to move data every time we encounter a target region, because this is just very expensive. We want to leave the data resident on the GPU throughout the execution. So this is where these pair of constructs come into play. These are the target enter data and target exit data constructs. So the way to think about this is that the device memory, the target device, has a sort of device data environment that it exists, and that we can manipulate that with these two constructs, the enter data and exit data. Now, also, when we copy data around and on target directives, that's going to copy data into this target, the device data environment, and then move it out again at the end of the target region. But between those target regions, that device data environment is going to exist if we've used these enter data and exit data constructs to set it up so that that's what happens. So these are standalone constructs. They don't have any Fortran body associated with them. They're just a single line of OpenMP compiler directive. So let's take this example at the bottom of the slide. So the first one, let's start in the middle and work outwards. So we have our time step loop, this do loop over T. It's going to inside that loop, we're going to be having lots of target regions. So for this one, we just have a single target region that's going to be executed once for every iteration. So we're going to have n target regions that are going to be launched. Now we want to keep those arrays, A, B, and C, maybe our vector add, inside the device data environment for all of the duration of that target region. So to do that, we're going to, before we go into our loop, we're going to use a target enter data construct. Now to do this, we just say OMP target enter data, and then this is where we add the map clauses that we've had from before. So this is essentially breaking up the behavior of the target directive into two. So when we have a target, it transfers execution and it transfers data. On a target enter data, we just do the part of that offload that just sets up the transfers to the device that you would normally encounter when you reach a target directive. So here it's just doing any data mapping that you do at the start of a target region, and this is going to set up this device data environment for us. So we have OMP target enter data map, and we're going to map to the device from the host the three arrays A, B, and C. At this point, this is going to trigger this memory copy on that construct so that the arrays get copied from the host to the device, and they're going to stay there until they're told otherwise. We can now run our time step loop, our T loop, lots of times, and it's going to have these target regions that execute. And when they start running, those target regions inherit the existing data environment, however it's been set up from before. So this means that inside that target region, it already has the mappings of A, B, and C already been mapped to it from this enter data that's happened before. This means that we don't have to do the bulk transfers of A, B, and C. Now, what we do is we map any pointers and any metadata that happen with A, B, and C, the same as we would with scalar variables as first private, but they just go as kernel arguments to the target region. So we don't really observe this overhead. But it does mean that if we have pointers, say, and I'll come on to this in a moment, the pointer values are going to be mapped correctly as we want. So we now have our target data environment set up with the target enter data. We've then left the data there and run lots of target regions on it. And now we want to bring back data from the device. And for this, we could use the target exit data construct. And this performs the functionality that would normally happen at the end of a target region for moving data from device to host, or maybe deleting data or something like that. So for this, at this point, we would bring data, the array C, because I've said target exit data map from C, and this would copy C back to the host and then remove C from the device data environment. So in this way, you can see that we've now severely limited the amount of memory transfer that happens, and we've isolated it outside of the key time step loops that it only happens once. We copy data once, use it lots of times, and copy back what we need at the end. So for vector add, this is how I might do that. I might allocate A and B and C. I have 3 arrays on the host that I need to allocate the memory for. And then initialize A and B on the host. Again, this is using just some Fortran vector notation, just as a shorthand on the slide. I then need to copy and set up my device data environment. So I know in vector add in my kernel, about 2/3 of the way down this slide, I'm going to be computing A plus B and setting it to be equal to C. So that means I need to make sure that the device data environment has the initialized arrays A and B, but also space for C. But I don't need to copy any array for C because I'm going to be writing to it only. So to do this, I'm going to be using my target enter data construct. So I have OMP with a sentinel before, target enter data map, and I'm going to map from the host to the device the arrays A and B. Then I'm also going to allocate, so with a map alloc, I'm going to allocate space for C. That's going to be the same size as the C on the host. And then I'm going to have my, my target region, my target teams distribute parallel do. And that's going to be my target, my kernel essentially. It's going to run vector add in parallel across all the parallel parts of the GPU as mapped by my compiler, and compute the addition of A and B and store it in C. So at this point, some data is going to be evaluated and be copied and mapped to the device because it's a target region. But A, B, and C, the actual bulk data already exists. The values A, B, and C, essentially the pointer values, they're going to be mapped essentially as a 0-length array or first private as kernel arguments. You won't notice them as a memory transfer. Finally, there's the variable n. N is a variable in my iteration space, as in my loop, my do from 1 to n. N is going to be mapped because it's a scalar. Remember, that gets mapped first private. Again, that's just a kernel argument, so we don't see a map for that. This means that when that target executes, there's not going to be any memory transfers triggered as a result, which is exactly what we want. We've set the data up, we run the kernel, do the computation, and then later at the end and the bottom of this slide is when I'm going to copy the data out of the GPU back to the host, and it's the array C. So we've allocated C beforehand. We've now filled it full of data inside the target region, and we're now going to copy the data back to the host using this exit data, and that's going to remove it from the device data environment because essentially we're at the end of the program. Now I could also delete A and B from the device data environment as well at that point. So with data existing on the device for a long period of time, there may be times when I need to move data between the host and the device on other occasions. Those occasions are when I don't want to create more sort of nested device target data regions, or I don't necessarily want to run a kernel on the device. I just want to move data between. An example of this could be Halo Exchange, and I'll show you that coming up, or maybe some file IO, something like that. The idea is the host is going to want to do something with some data between two target regions. So I have a target construct that updates data. I want to bring it back to the host to use it on the host for MPI, for file IO, something else, a library call to my favorite library. And then I then need to continue on the device after that. So the update construct, this is another one of those standalone constructs that doesn't have any Fortran code associated with it in a structured block. It's a standalone line. And we can use these to move data explicitly between the sort of host and device in either direction on demand. And remember, this direction is always from the host. So it's to from the host to the device, or from the device to the host. So it's a to mapping is host to device. The from mapping is from device back on the host. So this example here is how I may use the update construct. So I start off on line 1 with one of these enter data constructs. It's going to set up and copy the arrays A, B, and C to the device. So it's going to copy the memory that's been initialized on the host and copy it to the device. I then have a target region on lines 2 to 4, and that's going to use A, B, and C. And let's say inside that target region, I'm going to update A. I might have computed a new value of A based on the old value of A and maybe some B's and C, what's in B and C as well. I then need to take the A array and move it back to the host, maybe because I need to do something to it. And what I need to do on say line 10 is just an example of something I could do. And I might need to change it to a specific value that I've received a message over MPI from. So to do this, you can see on line 7, the update construct. This is OMP target update, and it says to so copy the data from the device to the host and I want A, and it's going to be the whole array from 1 to n. Now, again, I could have left the array notation off and just used the variable name A. So at this point, this is going to essentially trigger a memory copy between the device and the host. The notation here is also interesting. We no longer use the map clauses. We just use a from clause to signify the direction, because update really captures everything we need. We're updating the memory and we're moving memory from the device to the host, and then in brackets is what we're moving. On line 10, then I just update A to be something. You could imagine that this was actually just a Halo exchange routine where I've done my Halo exchange and I need to repack my buffers, and I've got new information to put back in the array. Then on line 13, this is where I transfer that array and copy the data there, the updated data, back to the device. And this is where I also use the update construct. So on line 13, we have OMP target update to, and this maps data from the host to the device. It copies it as another memory copy from the device to, from the host to the device. This is going the other way, host to device. And again, it's mapping the whole of array A. And then that means then that the device data environment now sees the updated copy of A because it's received it from the host. So in this second target region on line 15, we've got the updated values of A along with whatever B and C were on the device when we last left them. Finally, at the end, I might exit the data region and copy data back from the device. So these update constructs are very useful for in combination with the enter and exit data constructs for us to enable to initialize all the data on our device at the start of a run lots of kernels using the target regions, and then ad hoc and on demand move data between the host and the device as required for interoperability with other things, for example, a Halo exchange routine using the update construct. So this is exactly that example with a typical Halo exchange pattern. On line 1, I set up my data on my device, my target enter data map, and it's going to copy all my initialized arrays to the device. Between lines 3 and 16 is my time step loop, where I'm going to run a kernel and then do a Halo exchange and then run a kernel again and keep going until I've done enough time steps. And finally, on line 18 is when my simulation's done, and I need to clean up the device data environment and copy back everything I need, all the computed values. So inside the time step loop on line 4 to 6, I have my target. That's going to run my main kernel. That's the main computational part of this code. And then in order to do a halo exchange on line 9, I have my target update. And it's going to be a target update from. That's going to copy the data, this array that I might have packed inside the target region called halo. And that's going to copy it from the device to the host. So it's from device to host, this halo array. So now the host has got an updated copy of this halo array called halo, which I might exchange using MPI with an MPI send receive and whatever arguments I need to do that. Because I've then received some data, I now need to copy that data back to the device. So this is where I have my OMP target update to, and that's going to give the device and send that new updated value of the halo array back to the device, ready to run the kernel that's going to use that data in the next time step iteration. So you can see with just this update, and along with the enter data and exit data, we have quite a powerful way of directing exactly when memory needs to be transferred. We can set everything up, run lots of target regions on it, and then copy data ad hoc using the update construct. So pointer swapping. This is important in Fortran 2, especially when we consider the way that the Stencil code is written. They are just pointers that we can then swap between two arrays, the temporary array and the sort of a read-only and a temporary array. So it's worth noting that the mapping of the pointers occurs when that target region is sort of encountered as from the host perspective. So this example here sort of captures in a nutshell what's happening with the Stencil code. And when we start optimizing for data movement, this may be how it could look. So on line 1, we have data environment set up with the target enter data. Have a loop and a number of target regions that will run inside that. And I've just abstracted that away on line 5 to whatever it needs to do, along with the end target that's missing on this line too. And then I have a pointer swap. This is just a regular pointer swap. So when I re-encounter the target region for t equals 2 on the second iteration, A and B now point to the other places. Now that's fine because those get sort of evaluated every time the target construct is encountered. We're not mapping them. We're just checking what the mapping between the host and the device memory spaces are. And this is done by the compiler and the runtime. So this means that inside that target region, we will observe that A and B have been swapped, even though we've swapped them on the host. When we encounter them on the device, we'll still behave as if they've been swapped there as well, because it's just a pointer swap. That idea propagates over there because of the way that the targets are evaluated. It's worth noting that there's a slightly thorny, slightly tricky sort of issue you could run into. If you have a target region that you map from data and then the pointers change inside the target region, then the data will be mapped from to wherever it was pointing to when that from was encountered, which was at the start of the target region. So this is a slightly thorny issue that's you're unlikely to run into if you use these target enter data and target exit data constructs as well. So asynchronous offload. So far, we've had the host just sitting idle whilst the device has been executing, but we can have a way of the device, the host carrying on and continuing whilst the target region is being busy executing. So for this, we have the no wait clause to the target region, and this means it gets offloaded as a task. At this point, we must use all the OpenMP tasking semantics, such as using task wait or a barrier or something on the host, depending on how you've designed your application for these asynchronous tasks, whether you're using dependencies or task wait. So as an example for this, let's say I have a big amount of work to do on the GPU. So I have target no wait, and then my parallel loop over a very large number. And then I have my two end OMP end for those things. Now the host is just going to continue because of the no wait, and it's going to call some expensive IO routine that's completely independent to whatever work's being done on the target. I then, on the final line, line 13, I call OMP task wait. That should be a K, task wait. I'll fix that typo. And at that point, any of those tasks that I've had executed before, so this target no wait, at that point, my host will wait until that target task is finished before I can continue on doing something else. So that's an example of asynchronous offload. So let's talk a little bit about compiler support. So Cray was quite early in adopting support for NVIDIA GPUs in the end of 2015. As you've seen and what we've been using today, the latest version of CCE now supports all of OpenMP 4.5 and some of 5 in both C and Fortran and C++ as well. LLVM and Clang often has a lot of the bleeding edge implementations of OpenMP 4.5 offload, and in particular for NVIDIA GPUs. And it's used as the base for many compilers, including for Cray. A lot of that work originally came from IBM with their Excel compiler suite, and they contributed a lot of the work of the early work into LLVM. The Intel compilers originally began supporting OpenMP Target for their Xeon Phi co-processors back in 2013. With compiler, a couple of years later in compiler version 17, they supported OpenMP 4.5 for Xeon Phi. But then with their latest One API suite of compilers, tools, and runtimes, the One API suite now targets Intel GPUs with OpenMP. So using these same compiler directives that you've seen today, you're able to target NVIDIA GPUs and Intel GPUs. Now, the GCC compiler has had OpenMP support for lots of different architectures, and with the latest version 10.0, it can have target for the Xeon Phi, AMD GPUs, and NVIDIA GPUs. AMD also provide their own OpenMP compiler for AMD GPUs. So this really is a cross-platform, portable, parallel programming model that is an open standard. OpenMP is a standardized model, and all the vendors are contributing to that standard. So that it is possible to write an OpenMP program that will target GPUs from all of these 3 vendors. And if we look at the large machines that are going to be installed in this sort of exascale era, we're going to see lots and lots of Intel GPUs, lots of AMD GPUs, and lots of NVIDIA GPUs, particularly in their sort of machine learning and deep learning machines as well. Now, the best place to go and learn about the compiler support is on the OpenMP website, and the link to that is on the bottom of this slide. Now, I talked a little bit about NVProf before, and I'm going to show you a little bit of an example for that at the moment. Because with the Cray and LLVM, CUDA is used underneath the OpenMP implementation for targeting NVIDIA GPUs. So us as programmers will write OpenMP, and the compiler will turn it into whatever CUDA it needs to. And this means that it will use any of the infrastructure and tools that are provided by NVIDIA for their CUDA codes. So it can be useful to use the vendor tools for CUDA to understand what's happening with your OpenMP code. It's particularly useful because in OpenMP 4.5, although there's been some environment variables added in 5.0, that mean that if your target region doesn't get executed on the GPU, it can silently fall back to the CPU, and you can control that behavior in 5.0 now. So this is an example for the Stencil target code of what NVProf might look like. So the top there, it sort of gives me a summary of how much time is spent in each of my target regions, and then how much time is spent in memory transfers. Now the target regions are slightly strange. They look a bit weird, and they're constructed because they don't really have a name. It's just line numbers and stuff in our code. And that's exactly how they're expressed here. We have a file name and a line number. So you can see that most of the time is being spent on line 49, which is that target region in that particular file, my Stencil target file, for instance. If we add the print GPU trace, then this is going to print a nice timeline of exactly what's being transferred at any given time, which is very useful information to help tracking if we have any of these spurious memory transfers. So it's worth me saying at this point that the result of a reduction, if you use a reduction clause on a target region, then in OpenMP 4.5, that is a scalar, typically a scalar. If you don't specify it in a map clause, then that scalar is just mapped first private. This means we won't get the result, the reduction result back on the host. So it's very important for reductions that we have a map to from with the reduction result if we're targeting OpenMP 4.5. In OpenMP 5, they've changed this and they've made that the default behavior. So if you specify a reduction clause, then the reduction result is going to be mapped to from. So that's an extra thing to think about with the reduction clause. So we now come up to the final exercise for the day, and this is going to apply the things that we've been talking about in the last two lecture sessions, before the coffee break and after. So we now have a 5-point stencil code that is running on a GPU, but there's no parallelism that is exposed there. So use the target team's distribute parallel do construct to add parallelism to the kernel. And also we are moving lots of data around every iteration. So change the code so that it only maps the data to and from the device using the target enter and exit data constructs before and after the iteration loop. Again, make it do this reduction and print out the grid sum for every iteration to make sure it gets the right result. So this means you need to use the reduction clause on the team's distribute parallel do. And it means, as I just said, you need to use the map clause on the target around the exact kernel to copy the reduction result, the scalar, back to the host so that we can print it out or check it for convergence or something like that. It's useful at this point to start to have a play and use the system and try things out and see how things go. So experiment with different variations of the construct. What performance can you get by using teams distribute? What performance do you get if you use target parallel do? What if you have teams distribute parallel do SIMD? All those sorts of things. Try the different combinations and see what you get. You can also profile the code with nvprof to help explore the mapping. Have a look in the list.lst file that gets output by the compiler with the right compiler flag that's in the make file already to see what that mapping is like. It's also good to use the collapse clause on our two nested do loops so that you can increase the amount of parallelism. So play with using the collapse clause and not using the collapse clause and see what sort of performance you get. So that's the goal of this exercise. Do get back onto Isambard and have a play, and hopefully you're able to now start taking your code that you've started getting to run on a GPU and start optimizing it so it runs in parallel and with improved memory transfers. So there's lots of time to do that. At about 25 past 4, I'll start showing you a little bit about how I might have done that and wrap up for the end of the day at 4:30. So we've got just over half an hour now to do this exercise. So I'll pick up all your questions in the Q&A, and I'll see you at 25 past 4 UK time, at 16:25. We're about halfway through the exercise time now. Around sort of 25 past, I'll start talking a little bit about the solution, and then a short wrap up before we finish at 4:30. So keep asking questions on the Q&A. I'm happy to take all sorts of questions about OpenMP and even any that you had from CPUs this morning. Use it as a place to start discussing things as well if you're interested in that. I hope you're all getting on okay with parallelizing and optimizing the data movement for the 5-point stencil on the GPUs. Okay, we're drawing to the end of the tutorial today. And before we finish, I'd just like to do a couple of things. First of all, I'm going to show the sample solution that's available in the GitHub repository. And then just got a couple of things to talk about OpenMP 5, specifically related to the target directives. And then finally, just talk a little bit about tomorrow, the OpenMP talks that you'll hear at the user group tomorrow. So to start with, let's have a look at the sample solution, perhaps. So this here is the code that is in the stencil_target.f90 code in the repository. And this contains the sort of optimized version for running on the GPU. So this has the memory access patterns in it in the right way from, if you've followed us all the way from 9:30 this morning. It has principally, if we walk through the whole code from the beginning, once our data is initialized on the host on line 39, we're going to set up the device data environment. So we're going to have a target enter data, and we're going to map our two arrays, A and A temp, to the device data environment. We then have our time step loop that we iterate through a number of times, and we have our target directive. This is going to offload these loops here, the execution of those loops onto the device. Note that we have a map statement here. This is going to map the scalar total to and from the device every time this target region is encountered and executed. This is important because otherwise total would be mapped first private as it's a scalar. Then on line 50, I have our big directive, the teams distribute parallel do. That's to run the loops in parallel and spread them out over all the processing elements of the target device, our GPU in this case. I have a reduction clause with the sum operation and on the variable total. This is going to be computing a reduction over the variable total, and it's going to use the plus operation to do that. I then have the collapse clause, and that clause is going to collapse the next two do loops, the tightly nested do loops it encounters, so that we can spread nx by ny parallelism across all of the GPU. So with a 4,000 by 4,000 grid, that's 16 million iterations of the loop. We're going to share those amongst all the processing elements of our GPU. Plenty of parallelism there. It's going to do a reduction for us. We haven't had to implement our own reduction and copy the result back stored in total onto the host, ready to be printed out on line 61 here. Note on line 57, I undo the ordering of the directive. So I end the teams distribute parallel do. Note I don't need any clauses on that. It's just the constructs that I end. On line 58, I have the end target, which ends the offload and returns execution back to the host. I then swap the pointers on the host, and there was a question in the Q&A about this. So when this loop here, the time step loop, goes back into the target region, then this target region will reevaluate what A and A temp point to, and it will give the target region inside there then the updated values and use those pointing the other way around. So pointer swapping works exactly as we'd expect. We swap on the host and we then use those pointers as if they were a sort of function call sent through as function parameters to the device inside the target region. At the end, we then copy back the updated arrays. In this case, I've just copied everything back. So I've got this target exit data map from A and A temp. And that's it. The rest of the code just remains as it did in the serial version. So we've come an awful long way today. We've started with serial Fortran. By lunchtime, we had a vectorized, NUMA-aware, parallel, optimized code of a 5-point stencil running on the CPU. And then this afternoon, we've taken that code, and if you've joined us there, you joined us on at that point, and we've parallelized this 5-point stencil code on the GPU. We've got it running fast. We've got it using lots and lots of parallelism with this with the parallel constructs. We've thought carefully about the movement of data between the host and the device, and we've been using the device data environment and updating it and manipulating it with these target enter and exit data constructs. So that's brilliant. We've come an awful long way today. So thanks a lot for joining us and for sticking with us all this time. And you've done brilliantly well. And there's been a lot of information here. This is actually most of the OpenMP5 specification. The biggest omission to OpenMP that I haven't really talked about today is tasking. So if you're interested in that, there's a few slides that I've shared in the repository that you can have a look at about that. And there are some good books which I'm going to talk to in a moment as well. So it's brilliant that you've all stuck with it this far, and it's great to see you all learning to use OpenMP to write fast parallel codes on CPUs and on GPUs. So that's been brilliant. So to finish up, I'd just like to talk a little bit about OpenMP 5 and a few things that are coming in there. So I'll just get those slides up. Here we go. So OpenMP 5 is kind of an evolution of some things that were in OpenMP 4.5 that we've been doing today. And those things really help writing these performance portable programs a little bit simpler. And specifically around target, there's a few things I'd like to call out. And on this slide, there are those main things. So there's some things like the loop construct that helps us express parallelism in a more character-friendly way, just in fewer characters. There's things like mappers, which are really useful for C++ and derived data types. There's unified shared memory, which helps us initially start porting code to the GPU. We leverage hardware support for moving data between the host and the device. So we can remove all our map clauses at the expense of having to use unified shared memory. There's also things like reverse offload for offloading back to the host, and also this OMP target offload environment variable, which is useful to ensure the behavior is such that we make sure that the device isn't allowed to silently just revert back to the host, for instance. The other kind of key information is that in 5.0 implementations, reduction variables are implicitly mapped to from, so we don't have to remember to put that on the target directives ourselves. So let's talk a little bit about loop. OMP loop is a construct that's been added in OpenMP 5, and it says that the iterations of the loop may execute in any order they like, including being executed concurrently. So this allows our compiler to figure out how best to utilize the parallel resources. So this is somewhat similar to just using a target teams distribute parallel do SIMD, but rather than expressing it in that many characters, we can just express it with 4 with loop. So for the target, I might have a OMP target and then OMP loop and decorate the loop there with that. And it's just going to run that loop, hopefully in parallel on the target device. So that's a convenient addition to OpenMP 5. There's also unified shared memory, and this is leveraged with this requires construct that's been added to OpenMP. This allows us as developers to make a statement that we require a particular feature of the OpenMP specification in order to guarantee that the code that we've written is going to be correct. So for here, say I want to allocate an array A and I allocate it on the host. If I say that my program requires unified shared memory, this means that the next bits that follow mean that I need to use that assumption. That is, that memory can be shared at the page level between host and the devices. And there is hardware support there in order to move pages on demand as memory is accessed. So this means this array that's been allocated on the heap is allowed to just simply be used on the device as long as I'm requiring the use of unified shared memory. So notice that I can have a target region that does something with A, either in a sort of simple subroutine or something, but I haven't had to map. So there's no map clauses here, and data is going to be shared between the host and the device. Now, if you have modern enough hardware that can support unified shared memory, this is a good way for getting a large legacy application running on the GPU. And then later, we can then start optimizing those memory transfers by using map clauses and setting up the device data environment ourselves. But it's a useful way to get started. So with that, we come to the end of sort of the main content of the tutorial. There's 2 really brilliant books on OpenMP that have been released in the last few years, both from MIT Press. The first one is called The OpenMP Common Core, Making OpenMP Simple Again, by Tim and Helen and Alice. that's a really great introduction to the kind of the key parts of OpenMP, many of which we've talked about this morning. So if there's more information and you'd like to dig more into that, I can highly recommend that book. Then moving into the more advanced things, some of which we talked about this morning, things about non-unified memory access NUMA, non-uniform memory access NUMA, SIMD, maybe some hybrid programming, and also some information about programming GPUs. There's this using OpenMP, the next steps book, also from MIT Press, from Ruud, Eric, and Christian. Again, I'd highly recommend that. The OpenMP website is a great place to also learn more about OpenMP and to find links to some support forums and things like that. You can download the specification. Now, the OpenMP specification, its intended audience is for the implementers of the standard, so people that write compilers and people that write runtime. So it's not really for the faint-hearted, but it's not totally unreadable. So if you are really interested in the kind of very low-level details of all the rules and regulations about what each of the constructs mean, the specification is worth looking at. There's also summary cards, which someone very helpfully posted a link in the Q&A for us this morning. There's that list of the compiler support, along with other tools and things that vendors provide. And there's also the advanced code, the example code, which goes along with the specification to provide examples of how to use all the different directives. That's a very useful PDF document. There are examples there in C and Fortran for all of the directives in the standard. Finally, there's an up-to-date list of all the books as well. So the OpenMP website is a really great kind of place to go and find out, and as a launch pad to lots of OpenMP. Now, before we finish, I'd like to just talk a little bit about tomorrow. This is the OpenMP users group, and tomorrow we're going to be continuing and having lots of really interesting talks from lots of different people. So I'm just going to share the agenda with you now. Hopefully you can see that. So we're going to start off at 1:30 tomorrow afternoon, that's UK time, and there's lots of really great talks all afternoon. In particular, for those of you that have joined this afternoon and are interested in programming GPUs with OpenMP, at 15:20, we've got a talk from NVIDIA who's going to be talking about best practices for using OpenMP on NVIDIA GPUs. But as you can see, the whole talk agenda looks really exciting. Lots of great talks about OpenMP from the vendors and from users and from universities and big labs like the Met Office, where they are using OpenMP for big simulations for real. The afternoon, there's going to be a really interesting panel discussion chaired by Jim Cowney, and we'll be able to have a good amount of time there talking about OpenMP. So thanks everybody for joining. Tim who's been fantastic at organizing the OpenMP user group this year. He's going to be reaching out to you all with a quick survey for asking you for feedback about the tutorial today. I'd really appreciate it if you filled that in and gave some feedback to me so that we can hopefully run this in the future and in an improved form. And we do take all the feedback really seriously. So thanks everybody for joining today. I hope you've enjoyed it. Fill in the feedback, and we'll see you tomorrow afternoon for the rest of the OpenMP user group this year.